Welcome to NPTEL MOOCs course on Computer Vision and Image Processing, Fundamentals and Application. Already I have defined mathematically the image. The image is represented by fxy. Fxy means intensity at a particular point. The point is x, y. That is called the spatial domain representation of an image. In an image, we have frequency information. Suppose if I consider edges or the boundary, that is nothing but the high frequency information. In edges in the boundary, there is an abrupt change of grayscale intensity value. That is why the high frequency information is present in the edges and the boundary. If I consider the constant intensity region, the homogeneous region, that corresponds to the low frequency information. So I can convert the spatial domain information into the frequency domain information for better analysis of an image. I can do some transformation. I can apply the DFT, the discrete Fourier transform. I can apply the DCT, the discrete cosine transform, like this, so that the spatial domain information can be converted into the frequency domain information. In case of the frequency, what is the definition of the frequency? Frequency means spatial rate of change of grayscale value. That is the definition of frequency. Now in this transformation, the signal is represented as a vector, and the transformation changes the basis of the signal space. That is the definition of the image transformation. And the transformation is quite useful for compact representation of data. So that means the image can be represented by using few transform coefficients. So I can apply DFT, I can apply discrete cosine transform, and the image can be represented by using transform coefficients. That means the compact representation of image, that is the image transformation. And because of this transformation, it is easy to calculate convolution or maybe the correlation I can compute, because convolution means in the frequency domain it is nothing but the multiplication. In spatial domain it is the convolution. So because of this transformation, I can easily do convolution. And let us see what is the meaning of the image transformation. So in my next slide I can explain the concept of image transformation. So in this block diagram you have seen the input is fxy, that is the image. After this we are doing some transformation. After the transformation I am getting FUV. So FUV is nothing but that is the transform image. U is the spatial frequency along the x direction and V is the spatial frequency along the y direction. After this we can do some operations in the frequency domain. That is the operation R I am doing in the frequency domain, and after this I am doing inverse transformation so that we will get the spatial domain information after processing. So I am getting GXY. So in case of the image transformation, signal data that is represented as vectors, and the transform changes the basis of the signal space. And one important point is the transform is usually linear but not shift invariant. And already I have explained that is it is useful for a compact representation of data, and because of this transformation I can separate noise and the salient image features, because the image is represented by few transform coefficients. So it is easy to separate noise and the salient image features. And also it is useful for image compression, because the image I am considering by only considering few coefficients that is which are more important that we are considering, and neglecting the remaining coefficients. So like this we can do the image compression. And the transform may be orthogonal or maybe the non-orthogonal. So suppose if I consider one transformation matrix, the transformation matrix is T, that is a complex matrix, and if I take the T inverse, that is equal to T complex conjugate transpose, then this matrix, the T is called the unitary matrix. It is called the unitary matrix, and in this case the transformation is called the unitary transformation. And suppose the T is real, the transformation matrix is real, then T inverse is equal to T transpose. Then in this case this matrix is called the orthogonal matrix. orthogonal matrix. So I have defined unitary matrix and the orthogonal matrix. Based on this condition, my transformation may be unitary transformation or maybe the orthogonal transformation. So transformation may be orthogonal if this condition is satisfied, or maybe the unitary, and if this condition is not satisfied, then in this case it will be non-unitary or maybe the non-orthogonal transformation. One definition is the transformation may be complete or undercomplete. What is the meaning of this? Suppose let us consider xn. I am representing the input data. Xn is represented like this. N minus 1, k is equal to 0 to n minus 1, xk and phi n k. And this is the basis function. This is the basis function. So my input data, that is input vector, is represented like this. Xn is equal to xk. That means I am doing some transformation xk, and the basis function is this. So in this case, k is equal to 0 to n minus 1. This xn can be approximately represented like this. This is the approximate representation of xn. So k is equal to 0 to m minus 1. Now it is m minus 1, xk phi n k. So in the second representation, that is the approximate representation, I am only considering k is equal to 0 to m minus 1. In the first case, I am considering k is equal to 0 to n minus 1. That means I am considering the n number of coefficients. That means x0, x1, x like this I am considering. But in the second case, I am considering only m number of coefficients. Then in this case, your m is less than n. M is less than n. Now, if I consider the first one, that my transformation will be the complete transformation, and if I consider the second case, that is the undercomplete case. And in both the cases, if I see, I can determine the mean square error. The mean square error is nothing but 1 by n summation n is equal to 0 to n minus 1 n is equal to 0 to n minus 1, and in this case the mean square error also I can determine. So a transform may be complete or undercomplete. So you can understand this. And another one is the transformation can be applied for the whole image. That means if I consider the whole image, this is the whole image, this is n by n image. So for the entire image, I can apply the transformation, or otherwise I can apply the block by block. So suppose if I consider this is the block, one block I am applying the transformation, next block I am applying the transformation. Like this I can apply the transformation, the block by block. So the transformation may be applied to image blocks or maybe to the whole image. So this is the definition of the image transformation, and the transform may be orthogonal or the non-orthogonal, complete or the undercomplete, applied to the image blocks or the whole image. Now based on this orthogonality concept, I can show you different types of transformation. So what are the different types of transformation? So image transform. So first one is I am considering orthogonal sinusoidal basis function. The first case is orthogonal sinusoidal basis function. The second case is orthogonal non-sinusoidal basis function. Or I can consider the basis function depends on the basis function depends on the statistics of the input signal. And another one is the directional transformation. So I can classify image transform like this. The first one is orthogonal sinusoidal basis function. My transformation function is orthogonal, and also I am considering the sinusoidal basis function. So examples like the DFT, the discrete Fourier transform, or the DCT, the discrete cosine transform, or maybe the discrete sine transform, DST. These are the examples. So basis function is orthogonal and also the sinusoidal function. Another one is orthogonal non-sinusoidal basis function. So I can give some example like the Haar transformation, Haar transform, that is we will discuss in the wavelet transform. In the wavelet transform you can understand what is Haar transformation. Other transform like Walsh transform, Hadamard transform, or maybe slant transform. In this case, basis function is orthogonal, but in this case it is non-sinusoidal basis function. Another case, the next one is the basis function depends on the statistics of the input data. Then in this case I can give one example. One is the KL transformation. I will discuss about the KL transform. And another one is singular value decomposition, SVD, the singular value decomposition. So I can give these examples. So basis function is not fixed, but basis function depends on the statistics of the input data, the input signal. That is the examples like the KL transform and singular value decomposition. And regarding the directional transformation, so already I have discussed about the Radon transform. That is one example is the Radon transform. And another example I can give, I will discuss later on, that is the half transform. Half transform. So I have this type of transformations. One is the DFT, DCT and DST, that is the orthogonal sinusoidal basis function. And another one is the Haar transformation, Walsh transformation, Hadamard transformation, slant transformation, orthogonal non-sinusoidal basis function. And another one is the basis function depends on the statistics of the input signal, that is the KL transform and the SVD, and directional transformation like Radon transform and the half transform. Now let us consider one dimensional sequence. The one dimensional sequence is xn. So it is n is from 0 to n minus 1. Now I am doing some transformation. The transformation is x is equal to tx. So this transformation I am considering. This x is the small x is the input data, and in this case the x capital is equal to tx. T is the transformation matrix. So I can write like this: xk is equal to tkn. Tkn is this. This is the transformation kernel. Xn is the input data, the input sequence. And in this case, if I consider the transformation is something like this, the T inverse is equal to T complex conjugate transpose. So already I have defined, this is called the unitary matrix, and the transformation will be the unitary transformation. And for the reconstruction, I can use this formula, that is reconstruction of the original sequence. Small x is equal to T complex conjugate transpose x, because the T complex conjugate transpose is nothing but T inverse. So in this case, the reconstruction formula I can get this. This is the reconstruction formula. So xn is equal to k is equal to 0 to n minus 1, T complex conjugate transpose k comma n xk, and this is the n is from 0 to n minus 1. Now let us consider this case, the x is equal to Tx. So x is the capital X, that is the transform data, T is the transformation, and x is the input sequence. So I have defined this one. So in the matrix form, I can represent in this form. So first one is the transform data. So this equation I am writing in the matrix form. So first one is the transform data, and after this I am considering the transformation matrix, and after this I am considering the input data. In this case, that x naught, this small x naught, x1, xn minus 1, that is the input data, and x naught, x1, xn minus 1, that is the transform data, that is the capital, and I am considering the transformation matrix. Now let us consider 1D transformation. So I think already you know the DFT. So how to write the DFT? So 1D DFT I am considering first, 1D DFT. So one directional DFT I can write like this: xk is equal to n is equal to 0 to n minus 1 xn e to the power minus j twice pi divided by n nk. That is the, and I can write like this: n is equal to 0 to n minus 1 xn w n k. So in this case w is the twiddle factor, you know w is the twiddle factor DFT, and xn I can write like this: xn also I can write like xn is nothing but 1 by n is equal to k is equal to 0 to n minus 1, k is equal to 0 to n minus 1, and it is xk w minus nk. So I can write like this. This is the 1D DFT. So in this case I am considering the data vector, this is the data vector, and I am considering the 1D DFT in the matrix form. So 1D DFT in the matrix form I can write like this. So this is the DFT already I have defined, the DFT 1D DFT I have defined, and in the matrix form I can represent like this. So this is my transform data, this is my and this is the transformation matrix, and this is my input data. And regarding the inverse one, if I consider the inverse DFT, so the inverse DFT is nothing but this is the inverse DFT, this is the IDFT. So inverse DFT I can represent like this, and in this case if I see this transformation, the transformation matrix is suppose W inverse is equal to W complex conjugate transpose and divided by n. That means as per the definition of the unitary matrix, the DFT matrix is not unitary. So it is not unitary. It is not unitary. The DFT matrix is not unitary. So I can make the DFT matrix unitary. If you see my second slide, you can understand this one. So I am defining the DFT like this now. So DFT is Fk 1 by root n Fn Wnk, and this is my inverse DFT. So if I consider this, then in this case my transformation matrix will be like this. So T inverse is equal to T complex conjugate transpose. That means in this case I am getting the unitary DFT. So this discussion, up to this discussion, you have understood that the meaning of the unitary transformation and the orthogonal transformation. In case of the unitary transformation, if I consider the unitary matrix, that means the T inverse is equal to T complex conjugate transpose. That is the definition of the unitary matrix. And suppose the matrix T is the real matrix, then the T inverse is equal to T transpose. That is the definition of the orthogonal matrix. And based on this, I may have unitary transformation or orthogonal transformation. And in this example, I have shown the DFT transformation. The DFT transformation is not unitary, but I can make it unitary. I have defined the DFT like this. So DFT is 1 by root n, like this I have defined, so that the DFT transformation matrix that will be unitary. So that is the definition of the unitary transformation and the orthogonal transformation. Now let us consider the unitary transformation and basis. So I am considering one transformation matrix, the transformation matrix is T, and I am considering the unitary transformation. So a transformation matrix is, the rows are like this: T00, T01, T0 n minus 1, T10, like this. I have the transformation matrix. Then what will be my T inverse? So I am calculating the T inverse. T inverse is very easy to calculate because it is the unitary matrix. So in this case I have to do complex conjugate, and after this I am doing the transpose of the matrix. So T inverse is equal to T complex conjugate and transpose. So I am getting T inverse, and after this I am showing the transformation here. So this is the input data here, and this is the T inverse. I have the T inverse, and this is the transform data, F0, F1, the capital F1. These are the transform data. Now in this case, this I can represent like this. Now in this case, the columns of T inverse are independent. So if I see the columns, these columns, suppose these columns, the columns of T inverse are independent, and they form a basis for the n dimensional space. So this column is independent, this is independent, this is independent, and I can give one example of the unitary transformation. Here the 2D DFT I am considering. So the transformation matrix is something like, suppose 1 by root 2, 1, J, J1. This is the transformation matrix. Then I can determine T inverse. The T inverse will be 1 by root 2, 1 minus J, J1. So this is my T inverse. So this is the definition of the unitary transformation. So already I have explained what are the examples of the unitary transformation. One is the DCT, one is the DST, discrete sign transformation, and one is the Hadamard transformation. And this KL transformation is also unitary, but in this case, in case of the KL transformation, the transformation matrix or the transformation kernel depends on the statistics of the input data. In case of the DCT, the transformation kernel is fixed, but in case of the KL transformation, the transformation kernel is not fixed. It depends on the statistics of the input data, but it is orthogonal. Now the properties of the unitary transformation: the rows of the transformation matrix, T form an orthogonal basis for the n dimensional complex space. That is very important property. And one important thing is the determinant of T is equal to 1. That you can determine, the determinant of T is equal to 1. All the eigenvectors of T have unit magnitude. That is another property. Tf is equal to lambda f. By using this you can determine the eigenvalues and the eigenvectors. So all the eigenvectors of T have unit magnitude. Another important property is the Percival's theorem. That means T is energy preserving. The transformation is energy preserving because it is an unitary transformation which preserves energy. That is called the Percival's theorem. So in this mathematics I have shown here, first I am calculating the energy in the transform domain. F complex conjugate transpose F, that corresponds to energy in transform domain. And another one is I can determine the energy in data domain, that small f complex conjugate transpose F, that is the energy in the data domain. After this you can see this mathematics, and if you see that this T complex conjugate transpose and this part, this is nothing but the identity matrix. I is the identity matrix. So from this here you can see that F complex conjugate transpose F, that is the energy in the transform domain, that is equal to the energy in the data domain. So energy in the data domain is this. So energy is preserved. The energy is conserved, but one thing is that most of the energies are unevenly distributed among the coefficients. So what is the meaning of this? Suppose after the transformation I am getting some coefficients. These are my coefficients, but the most of the energies are available in few coefficients. So these energies are available like this, and for the rest of the coefficients the energy is very negligible. That means energy is conserved but will be unevenly distributed among the coefficients. So the most of the energies are available in these coefficients only, and remaining, if you see the coefficients, the energy is negligible. So in case of the image compression, I can neglect this these coefficients, because image compression is nothing but the compact representation of data. So, I can neglect the redundant information. So, that is why I can consider only these coefficients, the coefficients having the significant energy I can consider, and remaining coefficients I can neglect. So, this property is very important, the energy is conserved, but most of the energies are available in few coefficients. The next property is the decorrelating property. So, in this property you can see the input data is highly correlated, but after the transform data will be less correlated, or maybe you can consider uncorrelated. So, input data is highly correlated, and after the transform data will be uncorrelated, that is the concept. So, if I consider this is my data vector, corresponding to this data vector I can determine the covariance matrix, and after the transformation I am getting the transform data. The transform data is F, capital F, and my input data is small f. So, for this transform data also I can determine the covariance matrix. The covariance matrix is CFT, and for this also I can determine the covariance matrix. So, in this case my original data is highly correlated, but after the transformation I am having the covariance matrix something like this. This is the diagonal covariance matrix. The off diagonal elements, all these elements will be 0. If you see this is 0, all these are 0, all these are 0. So, that means the off diagonal elements are 0, that corresponds to the perfect decorrelation. So, that is the meaning of the decorrelating property. So, after the transformation the transform data will be less correlated, or maybe if I consider the perfect decorrelation, then in this case the off diagonal elements will be 0. So, these are the properties of the unitary transformation. So, first property is quite important, the rows of the transformation matrix, they are independent and they form the basis for the n dimensional space, that is one first property. A determinant of the transformation matrix T is equal to 1, that is one important property. One is the Percival's theorem, the energy in the transform domain is equal to energy in the data domain, that is the very important property. Another property is energy compaction property. So, most of the energy is available in few coefficients. So, after the transformation I am getting the transform coefficients, and most of the energy is available in the few coefficients. So, I can neglect the remaining coefficients for compact representation of data, that is called energy compaction property. And another property is the decorrelating property. So, my input data is highly correlated, and after the transformation the transform data will be uncorrelated or maybe the less correlated. So, if I have the diagonal covariance matrix, that means it is completely uncorrelated. So, these are the properties of the unitary transformation. So, in this example I have shown the first one is the image in the spatial domain. So, I have shown the pixel position and the pixels I am showing. So, you can see the correlated data, you can see the pixels, if you see the pixels. So, input is correlated, and after the transformation I am getting the transform coefficients, you can see the transform coefficient here. So, this portion is the transform coefficients, and in this case I am getting the uncorrelated data. So, that is the importance of the transformation. So, my input data is correlated, but after the transformation I am getting the uncorrelated data. Now, let us consider the 2D transformation. So, one example I can give, the 2D transformation mean in the image I can apply the 2D transformation. So, what is the 2D transformation here? So, first I am considering the data matrix F00, F01, F0 n minus 1, this is one row, like this another row is F10 and up to this F1 n minus 1. So, I am considering the data matrix. Next one is I am considering the transformation. I am getting the transform data, the transform data is Ft k1 k2, then in this case the Ft is the transform coefficients, and in this case k1 and k2 are the row and the column indices in the transform array, and I am considering the transformation kernel. The transformation kernel is T n1 n2 k1 and k2. So, this is my transformation kernel. Transformation kernel. And if I want to reconstruct the original data after the transformation, so in this case you can see, because I am considering the unitary transformation, that means the T inverse is equal to T complex conjugate transpose. So I am considering this kernel, so I can reconstruct the original data. Now let us consider one property that is called the separable property. So already I have defined the transformation kernel. The transformation kernel is this is my transformation kernel, and if I can do the separation like this, T1, one kernel is T1, another kernel is T2. So that means the transformation kernel T1, that is the kernel for the horizontal direction, and transformation kernel T2, that is for the vertical direction. So if I can separate like this, that is called the separable property. One important point is separable transforms are easy to implement. Why it is easy to implement? Because the transformation can first be applied along the rows, and after this I can apply the transformation along the columns. And in this case, if I consider the kernels along the rows and the columns have the identical function, then in this case I have the symmetric function, the symmetric property. What is the meaning of the symmetric? If the kernels along the row and the columns have the identical function, then this property is called the symmetric property. And if I consider the kernel for the 2D DFT, so this is the kernel for the 2D DFT, that is separable, you can see. So based on the separable property, you can see I can determine the 2D DFT by using the 1D DFT. So I can apply 1D DFT along the rows, and after this I can apply the 1D DFT along the columns because of this property, the separable property. So based on this separable and the symmetric property, and I am considering the unitary transformation. If you see, already I have defined this is the transformation, and Fn1 is my data, input data, the 2D data, and I am considering the transformation matrix. This is the transformation kernel I am considering, T is the transformation kernel, and I am applying the separable property and the symmetric property. So if I apply the symmetric property and separable property, I am having this one. So I can write this in the matrix form like this: Ft is equal to Tft. And what about the inverse transformation? This is my inverse transformation. T complex conjugate transpose Ft, T complex conjugate transpose. That is my inverse transformation, because I am considering the unitary transformation. So in case of the 2D transformation, 2D separable, and I am considering the unitary transformation, and also I am considering the symmetric transformation. This property again I am considering this property already I have explained. One is the energy preserving property, the distance preserving property, energy compaction property, and other properties like the decorrelating property. These properties are again applicable in the 2D transformation. And if I consider one image, the image is nothing but the 2D array of numbers, then again I can show you the 2D transformation. So I am considering one image block. The image block is x and the n1, n2, and that the size of the image is n cross n. So for the transformation, I am getting the transform data. The transform data is x, k1, k2, and in this case, this is my input image, and this is my transformation kernel. And what is my inverse transformation? Inverse transformation means I am getting the input image from the transform coefficients. These are my transform coefficients x, k1, k2, and this is my kernel for the inverse transformation. So this can be represented in the matrix form. If you consider this equation, there will be n square number of similar equations defined for each pixel element. So that means I have n square number of similar equations. So that can be represented in the matrix form. In the matrix form I can represent like this. So again I am writing this one. And what is my input image? The input images are like this. These are mainly the pixels of x, n1, n2. So I am writing this one, and this is my matrix. The matrix is H, k1, k2. So that is my matrix. So this H, k1, k2 is an n by n matrix defined for the variable k1 and k2. So the image block x can be represented by a weighted summation of n square images. So I am repeating this. So a particular image block x can be represented by a weighted summation of n square images, and each of the size n cross n. And the weights of these linear combinations are the transform coefficients capital X, k1, k2. and this HK1 matrix, this matrix is known the basis image. This is called the basis image. Now let us consider the 2D Fourier transform. So how to define the 2D Fourier transform? Here you can see. So I am considering my input image is fxy, and this is my DFT pair. So fxy, if I take the 2D DFT, then I will be getting FUV. The FUV means the Fourier transform of the input image. The input image is fxy, and this is my the DFT formula, that is in the continuous domain. FUV I can get from fxy e to the power minus j xu plus yv dx dy, and this is my inverse Fourier transformation. Now in this case you can see UNV. UNV is nothing but a spatial frequency in radian per length. What is U? U is the spatial frequency in the x direction, and V is the spatial frequency along the y direction. So in case of the FUV, I am considering two frequencies, one is U, another one is V, the spatial frequency. And for the Fourier transform, I think already you know this condition, that fxy should be absolutely be integrable. So this condition is important for the Fourier transformation. Now if you see this example, I am determining the Fourier transform of the images. I am considering three images, and you can see what will be the Fourier transform of these images. So first image is, you can see this is the first image. Corresponding to the first image, I have the Fourier transform, that I am getting the spatial frequencies. Corresponding to the second image also, I have the horizontal lines. Then in this case I have the Fourier transform. You can see these points here. And for this image also, the third image, I have the Fourier transform, that is the 2D Fourier transform. This Fourier transform can be represented in the polar form. That FUV is the Fourier transform, that can be represented in the polar form. So I have the magnitude part and also the phase angle. So I have two information, one is the magnitude information, another one is the phase information. And in case of the FUV, it has two components, one is the real part, another one is the imaginary part. That is the Fourier spectrum of the input signal. The input signal is fxy, and by using this formula I can determine the phase angle. Now in this example I want to show what is the meaning of the phase information and what is the meaning of the magnitude information. Phase information represents the edge information or the boundary information of the objects that are present in the image. And for the applications like medical image analysis, this phase information is very important. And what is the meaning of the magnitude? Magnitude tells how much of a certain frequency component is present in the image, and the phase information tells where the frequency component is present in the image. Corresponding to this example, if you see, I have the input image is fxy, and I have the two plot. One plot is the magnitude information I am plotting. So first is the magnitude plot, and second one is the phase information I am plotting. So in case of the magnitude plot, I am using the log transformation. I will explain what is the log transformation. Log transformation is used to compress the dynamic range of an image for better visualization. So you have seen here, I have two information, one is the magnitude information, another one is the phase angle information. And in this case you can see I am doing the reconstruction of the original image from the 2D Fourier transform. So in the first case I am considering the magnitude information, but I am not considering the phase angle information. Phase information I am not considering. And this is my reconstructed image. That means you cannot reconstruct the image only by considering the magnitude information. In the second case I am considering the phase information, but I am not considering the magnitude information. Magnitude is constant. Then also this is the reconstructed image. So in this example you can see that I want to reconstruct the original image by considering the magnitude information and the phase angle information. If I only consider the magnitude information, or if I only consider the phase information, the perfect reconstruction is not possible. So for perfect reconstruction I need both magnitude information and the phase information. And in this example I have shown the Fourier transform of a simple rectangular bar. So my input image is this, and corresponding to this I have the Fourier transform of this. Because for a rectangular function If I take the Fourier transform will be the sinc function. The second case I am considering Fourier transform of a simple image with Gaussian distributed intensity. So, if you see the intensity, this one, this is Gaussian distributed intensity. The Fourier transform of a Gaussian function is Gaussian. So, that means in this case also I am getting the Gaussian distribution here. The third example I am considering two identical objects placed in different spatial position, and corresponding to this, if you see this here, this object is placed here, this object is placed here. Corresponding to this, I am getting the exactly the same Fourier spectrum. The Fourier spectra I am getting. And in the last example, I am considering the rotation invariant property of the Fourier transform. So, this object is rotated. If you see, then in this case, if it is rotated, the Fourier transform is also rotated. That is called the rotational invariant property of the Fourier transform. So, up till now I discussed about the concept of the Fourier transform. The Fourier transform is quite important to see the frequency component present in the signal. So, in an image I have the high frequency information, another one is the low frequency information. So, in my next class I will discuss another important transformation, that is the discrete cosine transformation, and also I may discuss the fundamental concept of the KL transformation. In case of the Fourier transform and in case of the DCT, the transformation kernel is fixed, but in case of the KL transformation, the transformation kernel is not fixed. It depends on the statistics of the input data. So, next class I will discuss about the DCT and the KL transformation. So, let me stop here today. Thank you.